Welcome to another problem session. So this is we're doing this MCAT JEE prep, and this is probably a little bit advanced for MCAT, but not too far out of JEE requirement. But even for MCAT, if you have a little bit advanced understanding of something, it always helps speed up your problem solving time. Okay, so this is coming from Kleppner and Kolenko. Probably I'm going to do a whole bunch of Kleppner and Kolenko problems. They are really good problems, I had, students do this. All right, let's see. So here is a car on a rotating platform. So let's kind of here is a large platform. And so his axis about which this whole platform is rotating, fixed. And there's a line on the platform, and a car is supposed to drive on that line. So it's supposed to drive at that line at constant. So at t equals 0, the car starts really near the center and follows a line painted radially outward. So the car is going to go on that line. So his car is kind of rotating with the platform as well as moving outward. Some speed v0. Of course, the velocity is in space is kind of changing around, right? It's just going around like that. So I'd say sometime it's over here. At another time, the velocity is pointed. This thing will be over there sometime. This line painted will go there, and if it's over here, if the car is moved over here, so it's going to in that direction at that point, v0. But it's constant no matter what. It's always radially outward. Of course, the weight. So let's see. This is situation t. At situation t, and the weight of the car is w, which you can say mg. And the coefficient of friction between the car and the stage is mu. So this is let's call it static friction, so that it doesn't slide. Okay. Find the acceleration of the car as a function of time using polar coordinates. So this is about using polar coordinates. You don't have actually polar coordinates is the correct choice because of the way it is, but the problem is asking that, so we're going to do that way. And draw a clear vector diagram showing the components of acceleration at some time t equal to 0. So because we're doing polar coordinates, I wrote up here what the acceleration polar coordinate will be. So let's see, from looking from the above, we can redraw this picture a little bit. So it will look like this when you draw the picture. And let's draw a little bit bigger picture. So you have x and y, and we're going to draw at some time t. So let me get rid of this x and draw a new x. So this is x. Okay, so I drew a circle here, but of course the platform goes all the way here. This is the platform, and this is the radial direction. So at this time it's over here, and this radial r, and this is theta, this. And so if you look at, there are two directions, a direction radially outward this call. I have done denoted by u hat r, but sometimes you just denote r hat. R hat is a vector which magnitude is 1, as pointed out. If I was over here, the r hat will be pointed this way. So r hat depends on what time it is, okay? So where I am. I'm over here, then r hat is pointed that way. If I'm over here, the r hat is pointed that way. So it's not a fixed vector except that it's radially outward always. And then there's a tangent to that. This is the tangent part, and this is the radial part. And going increasing theta is increasing this way. If you go other way, theta decreases. And so this is the r hat, which theta hat, which I denote as u hat theta, unit vector. So theta hat is 1. So instead of u hat r, u theta hat, people just use r hat, theta hat for it. When I in my books, when I write unit vector theta hat, this like that. It's just for writing in a textbook. But when you're doing something, you don't do it like that. So if you work out the acceleration at this time, the coordinate is rt and theta of t. So that's the coordinate at that when it's at that point. That's theta, and this is distance r. So which is the same thing as x of t, y of t in Cartesian coordinate. But we're not going to use this, we're going to use that. So let's see. So if you work out the acceleration, I'm not going to show this. So rather than remembering all these derivatives, so you actually better remember is a dot. Dot will mean d dt. You have a double dot, that will mean d square dt square. You make that notation in your head. This is a Newton. Newton actually used this. Interestingly, there are simplifying notation that Einstein used for summation, that also when you do gravity, the Einstein way, very useful, or when you do relativity, is very useful. So if you write this in this notation, acceleration is very easy to remember. Let me see, just cut off for a little bit. Our double dot, of course you can have a triple dot, things like that in this notation, minus r theta dot, but it's squared, theta dot is squared in the r hat direction. And you're going to have of course every term will have some r. This doesn't have any r. It looks like has r but doesn't have r because the unit is 1. So you can see r hat is like that. There's no r there. Theta hat is no r there either. Okay, so this guy does not have r. So the r has to be somewhere, because the acceleration unit will be meter over second square, right? So meter has to come somewhere, so it's easy to remember. So now go to theta double dot, because you're going to do double derivatives, and turns out to be there are two factors of r dot and theta dot that come along, and theta hat. So these are unit vectors, this is direction. Okay, so it's asking find the acceleration car as a function of time using polar coordinates. So if this is the formula for acceleration, all I have to do is figure out what are these guys in this situation. So it is saying that it's going with v0 radially. So it's saying that r dot is v0 and it's constant. Okay, if it's constant, so this is just dr over dt. It also says r at time 0, t equal to 0 is 0. It was right at the origin, right over here. Okay, so these things are given. So we can just say r at any time t will be just v0t, right? Because just integrate this thing or just multiply this thing with constant, right? So this is the r part, is that. So all these r's we know. We know this guy. How about r double dot? If this is constant, then we also know r double dot going to be 0. So no acceleration radially. How about, so this thing kind of simplifies a little bit, knowing that. So 0 for that. And theta dot is how it's rotating, right? Theta dot, how the angle is changing. And it's rotating with the platform. It's not sliding or anything like that. So d theta dt is theta dot, and that's just it says omega, and that's also constant. That means if I take another derivative, if I do theta double dot, that's going to give me 0. So actually this is 0, this is 0, and this is minus r omega square. This r is that guy, v0t. So we'll come replace that, okay, r hat. And this other one is, this is 0 plus to v0 omega there. So it's really simplified. Let's write this down with v0t. So this is acceleration is minus v0 omega square t r hat. So this whole thing plus to v0 omega theta hat. So if you go out there, we can actually draw this vector. So there's it's because this minus is pointed towards the origin. Okay, so this is the centripetal acceleration part, and this is the tangential acceleration part. This is the centripetal acceleration, and this is tangential acceleration. I really like polar coordinates. It's really so beautiful, you know. I know students sometimes get, you know, they have difficulty handling this, but you know, when you do a lot of problems with polar coordinates, you start to see the beauty of it. All right, so if I draw it over there, let's redraw it, because I'm over here. I'm not going to draw a circle anymore. So this is the radial. So r hat is pointed that way, but this is negative that. So the radial acceleration, I'm going to point. So this would be the amount v0 omega square t. So it's going to get bigger as it goes outward. And now 90 degrees to that is the tangent. This is 90 degrees, and is in that direction is theta hat, and this is all positive. So let's look like that right now. So this is 2v0 omega. That's the length of this vector. So this is, let's call this a sub t for tangential, and let's call this a sub r for radial. So these are two vectors, so-called components. When you add this vector with that vector, well, of course you can draw the picture like that. So actual acceleration is in that direction. Of course, the numbers will tell you which way it is, right? So we don't know the numbers, we just know symbolically. So that's the actual acceleration. Okay, how big is the acceleration? I mean, you can go on the direction of it. The magnitude will be what? Magnitude of the acceleration? Magnitude acceleration will be, you have one component like this, and you have another component like this, and they're 90 degrees to each other. Then it's going to be square root of minus, oh, let's erase that. Square of this thing, v0 omega square t square plus 2 v0 omega square. So that's the magnitude of the acceleration. Okay. All right. And we can say what the direction of the acceleration was. Let's see. If this is the direction with the radial direction, if this angle is theta, so this theta is not that theta, okay? You can say if this is, let's call this phi, then over here, this angle here, it will be pi over 2 minus phi, because this direction and this direction 90 degrees to each other. So this angle is phi, then it's 9 phi, and this is 90 degrees. So that's the phi here. So we have situation like this. This is the A, and this is the AR, this is AT, and this is phi. So tangent of phi can be A of this direction, this side over that side, AR, and AT is 2v0 omega, and that one is the magnitude part. All the signs are taken over, so this part just v0 omega square t. So v0 cancel out, omega, one of the omega cancel out, is 2 over omega t. The omega is per unit time, and this is time, so this doesn't have dimension, right? So omega unit will be omega unit is second, and t unit is second, so they cancel it out. So this is dimensionless, and so you can get this. Given the values, you should be able to get this, right? So now we're just working with arbitrary time. We're doing a challenging problem, so we don't need to just all right. So it says find the acceleration of the car as a function of time, which we did in polar coordinates. Draw a clear vector diagram at some time t greater than 0. So that's what we did. Then there's a, so that was A. Find the time at which the car just starts to skid. Okay. So acceleration is this, okay. What is actually keeping the car from skidding here? Car is here. It's trying to move in that direction. So what are the forces on it? Well, this has to be static friction that's keeping the car from skidding, right? And so in this plane, in this XY plane, and then the Z-axis is pointed out. Let me redraw the picture because, you know, although I can see it in my head, so this is the XY plane, and this is the Z-axis coming using the right-handed coordinate system. Z is coming above, out towards us, you know, in this picture. So car is over here. What are the forces in the car? Well, there will be, this will be going behind. So this is towards the earth. And this is above earth. So this direction will be the weight, and then there will be normal like that in that direction. So there are these two forces, and in this plane, this is the platform. In the platform, the only force is in this, the only force in the platform is only force in the plane of the platform is static friction. You say, oh, how the engine force? No, there's no engine force. Our engine is trying to rotate the tire. The tire is going to push against the platform, and the platform is the one which is providing the force on the car. Okay, so engine is not providing a force on the car. Engine is part of the car. This is very important to understand. So a lot of the problems like that, Fs from the platform. How do we know that? Oh, well, you can say, suppose the platform is frictionless. What will happen? It will go nowhere. It's just going to tire just keep rotating and in one place. There was nothing to push forward or sideways. So we just saw that in this plane, acceleration is pointed that way, and this angle was phi, and we just figured that phi out, and magnitude was this. So that was the acceleration. When this acceleration, there's only one force. This is the only force that can supply that. And it's asking for at the instant that you would use up max of this guy. So when we look at this direction, so the z direction just gives me normal force equals to weight. And in the xy plane, we get Fs max must be equal to ma. Of course, the direction will be this with the. It would be very hard to figure out which way the static friction is. Is it static friction? Is the static friction this way, that way, that way? I don't, know. It could be anywhere in the plane. But this problem actually tells you a very important thing. It's because this is the only acceleration in the plane, and the only force in the plane is static friction. Static friction must point that way. Static friction must point that way. That's the interesting part of static friction. You should know that it will support whatever acceleration it needs to be supported, and that's the direction it will be. Okay, static friction, there's no necessarily a set direction. The Newton's law actually tells you what the direction it will be. All right, so that's our equation, and of course, because I'm using Fs max, it's going to be connected with the normal force. It will be connected with the normal force. It will connect with the normal force. Fs max will be static friction times the normal force, and normal force happens to be here weight. It's the same thing about normal forces. The magnitude of normal force is not fixed value. Okay, whatever the Newton's law balancing of the forces requires. Okay, so over here, these three things tell you mu s. I've started using small m for mass. Okay, is equal to mass times acceleration. So the a just cancels out. So this is the acceleration at any time t. This is the balance of the forces and the acceleration. And so let's see what we have. The problem that we have, I think I have to find time at which the car just starts slides. Yeah, acceleration is increasing, right? With time, acceleration is increasing, so force is increasing. Eventually it's going to go beyond this thing, so it's going to start to slide. So putting that over there, square root of v naught square omega to the 4 t square plus 4 v naught square omega square equals mu s g. Of course, you can remove this and square this side, bring this guy on the other side, and divide by this, take a square root. So t will be a square root of mu square g square minus 4 v naught square omega square. This whole thing divided by v naught square omega to the power 4. Is that what turned out? Yeah. So v naught omega is common to that. Okay, so that will be the answer. I'm not going to simplify it. You can do it. So find the direction of the friction force with respect to the instantaneous this. Just start slide. Show your result on equilibrium diagram. So we already did that. So this is the C part. It has to be in that direction. No? It has to be in that direction. Okay. All right. This was a challenging problem. So if you found this hard, that's good. You know, you learned something from doing a hard problem or watching a hard problem done on the board. I think I'm going to try to do some more hard problems just for, you know, benefit of ourselves. If you kind of like this kind of thing, problems, the way I'm solving, I wish you could subscribe, you know. And also you can check out my website. For, you know, I wrote some book a long time ago, and I maintain this website, Physics Bootcamp. And this was coined by one of my colleagues. Like, okay, why not Physics Bootcamp? All right, so lots of good physics here. Talk to you later. Bye.